Hello everyone, welcome to my channel. So today we're going to be going over some units, some past paper problems covering units 1 through 4 and 6. In this part we're doing MCQ, and in the future we're about to do FRQ problems. Okay, so don't forget to subscribe. Yes. So number 13. 3 coplanar forces act on a block. Which diagram shows the direction of the forces such that the block could be in equilibrium? So the definition of equilibrium means that the sum of all forces has to be equal to 0, and the sum of all rotational forces, or torque, or moments, is equal to 0. Additionally, that means that we have to look at each diagram and see if they satisfy both these conditions. So we can start with A. So A here, right? So we have let's look at the forces. So if we look at the y component first, it's the easiest one, because we know that the one going down here is just going to be weight, so we just have to look for a force that counteracts that. And if we look here, there is a vertical component of this vector here, which will try and counteract the weight. Additionally, there is an x component of this upside vector, and then there's a x component going the other way, and we can see that the f of y is equal to 0 and f of x is somewhat equal to 0. I'm doing a lot of assumptions that the magnitude is equal. You can actually make these with these types of questions, because the questions that are wrong have fundamentally wrong answers. The magnitudes don't really matter that much in this case. So if we look at A here, now we have to look at the moments, because we considered that the sum of f is equal to 0 for all of them, and then we just have to check the moments. If we look at this one here, right, it's going this way, so it's going clockwise. If we look at A here, it's also going to the right, so this is going clockwise, and since they're going in the same direction, they actually don't cancel out, so it can't be A. B. Okay, so let's do the same thing. Let's do the weight, and then it turns out there's a weight up here, so the f of y is equal to 0, and look at the x, and then like this. So even though the magnitudes look so drastically apart, this is still might be possible equal to 0, simply because that these are actually positioned different places on the cube. See, this one is positioned somewhat inside the cube, while this one is positioned like near the edge of the cube. So we can like somewhat like assume that it's 0, but we'll come back to it. So for B, we can see that this is actually going this way, and the perpendicular to it is like that. So in this case, this force is going clockwise. In this case, it's actually going the other way, so it's going anti-clockwise. So that means that the torque is equal to 0. So this is actually a valuable answer, because the sum of the torque and the moments, and the sum of the forces is equal to 0. But just in case, let's check C and D. So if we do our y component, there's one that goes down, there's one that goes down, and there's no one going up. So f of y is not equal to 0, and thus our C does not work. Let's look at D. If we look at our y component, we have one y component going up, one going down, and another one going up as well. It turns out that these will cancel out each other because these roughly look around half the magnitude, so it's probably right. F of x is going to be 0 because they are going only up and down, so there's no x component. What about the torque? Well, this torque is actually off-centered, right? And there's no additional torque provided by any other vector, So the torque of each one is actually not equal to 0. So D does not work, and then we're left with B. Number 14. So a wooden block rests on a rough surface of a board. One end of the board is then raised until the block slides down the board at a constant velocity v, as shown in the diagram. What describes the forces acting on the block when it's sliding down with constant velocity? So let's look what they're asking for. So they're looking for the frictional force on the block and the resultant force on the block. So you should know that the resultant force is actually based on the acceleration, right? Because this is Newton's second law, which is back in like unit 2 or 3 or something like that. But in the problem, it says that our constant velocity, sorry, I just had a brain fart, sorry. Our object is actually moving at a constant velocity, which means that the acceleration is equal to 0. So if we look at here, no matter what the mass of the block is, our acceleration is 0, and thus F is equal to 0. So there's no way that A and C work, because they say that there is a resultant force, when in fact the resultant force is 0. So we only have B and D left. Well, we can look at the frictional force. We know that frictional force is going in the opposite direction of what our movement is, right? So friction opposes movement, right? So if a car is going one way, there's going to be F of friction the other way. Similarly, if we have a block here going down the ramp, right, there's going to be a frictional force going up the ramp, right? So our answer is just going to be D, where it's going up the board and has a 0 resultant velocity. (15) A uniform rod XY of weight 10.0 newtons is freely hinged on a wall at X. It is held horizontally by a force acting from Y at an angle of 30 degrees to the horizontal as shown. What is the value of F? Okay, so if you don't immediately recognize this, this is actually a moment question where the moment is equal to the force times the distance from the pivot, I should specify. So it turns out that let's assign each of these distances to X. By center of gravity of the pole, since it's uniform, we can say that the weight of 10.0 newtons acts in the very middle of the rod, simply because it's very symmetrical and the center of gravity is in the center of everything. So we can say that our moment going this way, which is clockwise, is equal to the distance, X, multiplied by F, which is 10.0. So this is 10.0x. And additionally, we have F. So remember that moment means the perpendicular to the pivot, I'm pretty sure, and like the beam, basically. Perpendicular to beam. So if you draw this up, it has to be in this direction only. The other direction going this way is negligible. We don't have to consider that now because we're only looking for the perpendicular force on the rod itself, right? So we're looking for the vertical component. So ACW is equal to F times the vertical component. How do we get the vertical component of F? You just multiply by sine 30 because it's the opposite, right? And then multiply by the distance, and the distance is the entire thing, which is going to be 2x. So now we have these two, and since we know that it is freely hinged to the wall, we can say that these two are actually equal. So 10.0x is equal to F times sine 30 times 2x divided by x, 10.0 is equal to f sine 30. Actually, sorry. This is 5 because we divided by 2x, sorry. Right? So this is 5, and then 5 divided by sine of 30 is equal to f. Sine of 30 is equal to 1/2. So if we divide by 1/2, we multiply by 10. So this is equal to 10. So in this case, it's going to be C. Okay, so number 16. A non-uniform rod has a mass of 100 grams and a length of 50 centimeters. It is supported by a chain at its midpoint. The rod is held in equilibrium by having a mass of 60 grams suspended from the right hand end as shown. The diagram is here, yeah. The center of gravity of the rod is a distance d from its left hand end. What is the value of d? Okay, so we're looking for the meters here, right? So if this is the midpoint, say this is the midpoint, that means this distance is 25 minus d, and then this is 25. Carbonation, my favorite. Okay, so basically, we're told that it's held in equilibrium. That means that the sum of moments is equal to 0, and that means that the sum of clockwise moments is equal to the sum of anti-clockwise moments. So our clockwise moment is going to be this weight here, mainly because it's going this way, right? It's turning the beam clockwise, and then this one is going anti-clockwise, right? Sorry, that's the wrong direction. It's going this way, right? So, yeah, and it turns out like this isn't really the weight. The weight is here, and it's going down here and turn the beam counterclockwise. So these are like our two weights, and we just have to calculate their moments. So our moment is the force times the distance. It's a formula that you should know. So let's start with the clockwise first. So we know our mass is 0.06. So remember that F is also equal to ma. And in this case, the mass is 0.06 kilograms multiplied by 9.81 meters per second squared. And distance is 25 centimeters, and we have to convert that to meters, I believe. So 0.025, no, 0.25. This is because there are 100 centimeters in 100 centimeters in a thing. So yeah. Okay, so this is gonna be about 0.14715 Newton meters. And then our anti-clockwise is going to be 25 minus d. So we're taking this distance because we're going off the pivot, not the end, right? So we know that this is in centimeters, so we're going to have to divide by 100. So this is meters. And then the force, and we're given that the mass of it is 0.1 kilograms. Multiplied by acceleration. So this is like F, and this is D, right? I'm kind of confusing the variables here, but like this D right here is the D we're solving for, and the other D up here is talking about the general equation of solving for a moment, right? So if you calculate this out, you first initially get 0.981 divided by 100 times 25 minus d is equal to anticlockwise motion. And then we have to set those equal. So 0.981 or 100 multiply 25 minus 0.981 over 100 times d is equal to 0.1415. And then you get that around 0.91d is equal to 100 is equal to around 0.091d 981, and you divide by 0.981. So then you get d over 100 is equal to 0.01, I think. And then we can multiply by 100, and we get d is equal to yeah, I did this wrong actually. 0.0981 divided by 0.981. You should get 0.1, sorry. And if you multiply by 100, you get d is equal to 10 centimeters. And that is our answer, I think. A thin horizontal beam XY. Okay, number 17. A thin horizontal beam XY is freely hinged at a point Y to a vertical wall. The beam is held stationary by a cable XZ, which is attached to the wall at point Z. The beam supports a weight W at point X. The forces in the cable and the beam are FC and FB respectively. Which vector triangle represents the force acting on point X? Okay, so first thing that we should notice is that we should always have our weight going down. Okay, if we look at these few vectors, right, we see that this one actually goes up and this one also goes up. So we can immediately eliminate B and D. Now, we need to consider the cable force and the force of the beam. So we know that our cable force is actually pulling us up and like kind of like in, right? So in this case, we're actually going like this way. If you look at our remaining answer choices, these are actually the same, and we just only have to figure out whether or not these two are actually, we have to figure out which direction f of b goes in. And it turns out that I'm pretty sure you can try and add these forces, right? So, for example, if we look at it, we know our, so try thinking about it like adding forces, by the way. So the beam is kind of like just there, right? What makes sense is that our cable is pulling us upwards, right? And our weight is pulling us downwards. And then our beam is like kind of like keeping us in, but like keeping us out in the same way. So in this case, it's most likely going to be like this way, because you have this x component to cancel out, right? So in this case, it's going to be A. Number 18. A ball of mass m travels vertically downwards and then hits a horizontal floor at speed u. It rebounds vertically upwards with speed v. The collision lasts a time of delta t. What is the average resultant force exerted on the ball during the collision? So a common idea with these momentum problems, you can tell these are like kind of like momentum. It's because it's mv, right? You learn that P is equal to mv. So a common idea in terms of momentum is like force is equal to the change in momentum or the change in time, right? So what does this mean? So F is equal to the mass times the final velocity minus m times the initial velocity over delta t. In this case, we have to figure out which direction it goes, because this goes upwards, downwards, and then you have to see whether or not you have to add or subtract it, right? So let's draw a diagram. Our ball is here. This is our ground. We're falling, and then as we're on the ground, right, which direction does the ball go? In this case, the ball goes upwards, right? Because if you bounce a ball, it bounces back up. It loses some energy, but in general, the momentum is the same by principle of momentum, I think. Principle of conservation, but like it's like collision basically. So momentum is conserved, and it's going positive, right? So in this case, we know that it's actually going upwards, because if we bounce a ball, the force is going to push the ball back up. So basically, we can eliminate A and C. Additionally, now we have to see if we add or subtract them, right? So if we say that this initial velocity going down is negative v, and this final velocity going up is v, right? They're going in the opposite directions, so that's why they're negatives of each other. So if you do the calculation, right, the actual force compilation, the final is v minus the mass times the initial, which is negative v over delta t, and it turns out that it's like mv plus mv, which is the other velocity, and then delta time. So it turns out in this case we're actually adding our momentum. Yeah. Number 19. A stone falls vertically from rest. Air resistance is negligible. What is the speed of the stone when it has fallen through a distance of 0.4 meters? So this problem is actually a kinematic question. It's relatively straightforward Suvat equation compared to like other problems. How do I know this is a kinematic question? So they're asking for the speed, right? They give us that we fall a distance of 0.4 meters. We fall vertically, so we know our acceleration, and it's from rest, which is our initial. And this is s, and then our speed is v, right? So we have au, v, and s. In this case, the best Suvat equation is v squared is equal to u squared plus 2ac. So v squared is equal to u squared, which is 0 squared, plus 2 times 9.81. And our displacement is 0.4. Calculator. Oh, by the way, calc is short for calculator. I don't know if you guys know that, but it's a common shorthand notation. And then you get B. V is equal to 2.801428207. A uniform beam PQ rests horizontally on a support at point S. A rope is attached at one end of the beam. The rope has an angle of 60 degrees to the vertical and exerts a force F in newtons on the beam. What is the moment of Newton meters of the force about the point S? Okay, so we know that based on moments, the moment is always on the perpendicular line of basically the forces acting on, right? So we're only considering the vertical component in this case because it forms a perpendicular to the beam, right? Just said the same thing twice, but yeah. So moment is equal to force times distance. Since we know the entire beam is 2.5 meters, and this part is 0.3, this side is 2.2 meters. So our distance is 2.2 meters. Our force F is the perpendicular, right? So it's F multiplied by sine, because it's opposite. Sine 30 is equal to the moment. In this case, the moment is equal to F times 1/2 times 2.2 meters is equal to 1.1 F, which is A. Okay, 21. A car of mass 850 kg is traveling in a horizontal straight line. The diagram shows the two horizontal forces acting on the car in opposite directions. One force has a magnitude 1200 and the other force has a magnitude 1600 newtons. What is the magnitude of the acceleration of the car? So we know that acceleration can be modeled in the equation F equals ma. And if we solve this, F is equal to m equals to a. And we're looking for acceleration. So our force in this case will be in newtons. Our resultant force is going to be negative 16 plus 1200, which is negative 400 newtons. So on top, our answer is negative, or on top of the fraction is negative 400. Our mass is given, which is 850 kg. And this is equal to our acceleration. And if you calculate this out, you get about 0.47 meters per second squared is equal to A, negative, but they're asking for the magnitude. So you have to take the absolute value, or you take the positive value of this, so it's just going to be 0.47. Three forces act on a trap door. The weight W on the door, the tension T in the cable, and the force H at the hinge. Which list gives the three forces an increasing order of magnitude? Okay, so first things first, let's try and figure out the individual components of each one. So if this is like not moving, right, that means that the resultant force is equal to 0. That means the sum of the F of Y is also equal to 0. But if we look at each of these forces, we can see that the vertical component of WY, HY is equal to TY. So in this case, T is most definitely greater than W, and T is greater than H. This is because T also has an X component, which makes it even greater. Because like, if you take a triangle, right, X, Y, the tension here is square root X plus Y. And since this X exists on this T cable, it makes the magnitude even larger than WY and H of Y. So we know that T is going to be the greatest magnitude. And let's try and eliminate some choices. Nope. Oh, this one works. And nope. So A, B, and D don't work. I'm going to let this C. The diagram shows 4 forces acting on a circular disk, as shown. Each force has a magnitude F. 2 of the forces act vertically and the other 2 forces act horizontally. All 4 forces act in the same plane as the disk. No other forces act on the disk. The diameter has diameter d. Which statement is correct? So, the diameter is in equilibrium because the resultant force is 0, blah, 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 blah. Okay, so something we should know is that these are actually couples. This F and this F are couples, and these F's are couples because they go in opposite directions, and they have the same magnitude. So if we draw this, right, this is D, so each individual one is D over 2, or R, habit. A common fact for a couple is that the resultant torque is equal to the distance between the 2 couples, which is in this case D, multiply the magnitude of the thingamajiggy, of the force. So for each couple, it's going to be 2FD, and then since there's 2 couples, it's going to be 2FD. If we look at the problem here, it asks if it's in equilibrium because the resultant force is 0. Okay, so it is, the resultant force is 0 because if we see here, this is positive x, this is negative x, positive y, negative y, and if you add them all together, they're going to be 0. But equilibrium is both resultant force and resultant torque. So even though this is true, this is not necessarily the full definition of equilibrium. We know that our torque is non-equilibrium, or our object is non-equilibrium because we have a torque force that is non-zero. So C is not the right answer because we know that it's non-equilibrium. And B is incorrect because we know our resultant force is 0. So thus, we're left with D. Number 24. What is not a statement of one of the Newton's laws of motion? Okay, so this is actually one of the tricky questions that I've faced. So because I didn't know exactly what to choose. But yeah, let's read the problem. I meant the multiple choice questions, the multiple choice answers. Goddamn. If a body X exerts a force on body Y exerts an equal and opposite force on body X. So it turns out that this is actually the equal and opposite reaction that people learn. And if I'm right, I'm pretty sure it's Newton's third law. If no resultant force acts on a body, it has constant velocity. So this is Newton's first law. If an object has no resultant force, it will either stay in motion or move at a constant velocity. The rate of change of momentum is proportional to the resultant force acting on it, and it takes place on the direction of the force. Okay, so this isn't actually Newton's laws of motions. This is just saying momentum P is proportional to the force in the direction of the force. And it is indeed proportional. It's proportional to T. But yeah, this may or might not be the answer, so let's look at D. The total momentum of a system of interacting bodies is constant if there is no external force. So, this is actually the law of conservation of momentum, which is not Newton's laws. So in this case, the answer is D, I'm pretty sure. Yeah, so the answer is D in this case. I'm pretty sure C is right, mainly because F is equal to MA, right? And then you can kind of split this A into ms negative 2, right? So Newtons is equal to kg times ms negative 2. So then it's kg multiplied by m times s negative 1 times s negative 1. This is time. So then it becomes force over time is equal to Newton's, which is Newton's second law. It's kind of weird, to be honest, the way you get this, but yeah. Thank you for watching. I hope it's alright. If you think, wow, Brian is so weird, he's recording a physics video during Halloween, and yeah, I am weird, but like, I don't know, this is still like another day of work. So I'm here, I'm working, doing this for y'all, because I know some people are still struggling with this, and I don't want you to struggle type thing. So yeah, thank you, have a good one.